Hey scientists, welcome to today's problem-solving strategies. We're going to take you through a video tour on how we approach solving problems in class. Remember, at all times you can pause it, rewind it, stop it, come back to it. Here are our problem-solving strategies. The kids have a cool little yellow card. Here it is on the board. It runs through our primary and secondary strategies. The first primary ones begin with reading the problem, labeling, drawing the problem, writing down the knowns and unknowns, choosing the correct formula, checking the problem, and asking ourselves, is that solution possible? Our secondary ones that really go along with the first primary ones are, is our work neat? Did we show our work at all steps? Is our math and algebra correct? And lastly, did we include proper units? A problem we had recently was one where we considered echolocation in the hunting orca. We're given the velocity and we're given the time, and we want to know the distance. We're going to go through how it is we solve this. Oftentimes the kids look at new problems and they're challenged by it. They're not sure where to begin. These strategies aim to give kids a protocol, give them a practice with which to do it. Right? It's not unlike a baseball player. Every time they're stepping into the box, right, they're doing the same thing, whether it's adjusting their helmet, taking a look at their gloves, in and out of the box, or you could take it for hoops. Every time you take a free throw, right? For me in high school it was 5 dribbles. Right? It's that kind of strategy that we can approach every problem with. Right? So although there's an infinite number of problems, we can set about solving them the same each and every time. A lot of these strategies that I've come up with over the years originated in an AP physics book by Gian Coley. We can see equations such as these. By the end of first semester, we will have covered pretty much all of these formulas. And so as we go, we will add to the back of our card and make it more and more extensive as we add to the F formula section of our card, which you see right here. We want to consider this card our multi-purpose tool, right? Much like a Swiss Army knife, we can use these strategies and these formulas to solve any problem we've got. We want to be able to use it as scaffolding, right? To build up or construct our knowledge, right? Connect ideas, link one problem to the next, link our orca problem to an acceleration of a car problem, to free fall off of a cliff problem. We want to be able to use it to find patterns in the problems that we solve. Right? It's important to have strategies in all that we're doing, right? Consider it like we would have a strategy in a football game, or the way we'd approach the chessboard with a certain bit of strategy. Right? Or even where you get to a maze, something that's challenging, we've got no idea how to approach it. Sometimes you jump to the end, work your way back, and then go forward. Again, these strategies, solving every problem in a similar fashion, will end up being highly valuable to us. We can consider it like cooking. I told the kids earlier, we've got a set of ingredients. So far that means distance, time, velocity, acceleration. We then use those ingredients and we can apply them towards a recipe. So the egg, the flour, the chocolate, the sugar approaches a certain recipe. So far our recipes are seen in these formulas. We can then take our problem-solving strategies, as we see a little bit further written out here, abbreviated in primary and secondary on this sheet. And then finally, the ingredients to recipe, we cook and solve it. We eat, which is our answer, yummy, yummy, yummy. Back to this problem in our first steps. We're reading it. So consider echolocation and the hunting orca. How far away is the salmon if the sound travels at 1,500 meters per second and it takes 0.48 seconds for the orca to receive the signal? Our first step is we're labeling that problem. We're noting here's our velocity that's given. We're unsure of our distance, and we're given the time. Here's another set of problems from the other night of homework, where I used Notability to color code and label the problems. Right? What is given? So again, this is on the paper where we're labeling ahead of where we draw. Here are a few more examples. From our last test, what that would have looked like is here. Labeling our different forces. Force of scaffolding, force of the cat, force of Mario. And then I'm drawing the formula, or drawing the information out in a picture, and putting the knowns and unknowns right there for us to solve. Here's an example with some cannonballs. You can see again, on tests I'll put the problem solving strategies on it so they can follow it, and they'll also have formulas with them at all times. You can see a problem involving a giraffe. Okay, let's take a look at a real problem. This problem says, imagine you're driving a car at 30 meters per second. You see a red light ahead, and it takes you 5 seconds to stop. What is your acceleration? If we take a peek at our problem-solving strategies, we've already read the problem. Not a bad idea to reread it. And then we want to label it. And so I go through the problem and look for important information, starting with, we're at 30 meters per second. That information is a velocity. We read through it again, we stop at a red light, we see that coming up. We have 5 seconds for which we stop. The 5 seconds is our time. And it's important that we look at the information held in just the word stop. Because the stop is telling us that in the end of the problem, so our final velocity, we're at 0 meters per second. Which means it'd be a good idea to adjust the velocity we had at the beginning with 30 meters per second and label that as our initial velocity. At this point, we'll take a shot at drawing the problem out. Zoom in a little bit. Take a look at a fancy new car. This car is starting out at 30 meters per second. In the end, when it stops, it's at 0 meters per second, which is our final velocity. The time it takes to do this is 5 seconds. So at this point we have down what are considered our knowns and unknowns. Our next step is from this information to find what formula fits best. The formula for us is going to be acceleration equals change in velocity over time. And if we look back up in our original problem, that's what we're looking for. Right? That's the important thing. Right? What is our acceleration? Right? That is what we're looking for. So acceleration equals we don't know. Well, now we do. We can connect down here to our formula that A equals change in V divided by T. If we go further, that means the change in velocity is the final velocity minus the initial velocity divided by time. We can go underneath that and say, okay, cool. Our final velocity from our drawing is 0 meters per second. So 0 meters per second minus our initial velocity of 30 meters per second divided by our time, which is 5 seconds. We can then solve that equation. The top is going to be negative 30 meters per second over 5 seconds, which when we do the math comes out to 30 divided by 5, or negative 6 meters per second squared. This ends up being our acceleration. We can look back over the entire course of the problem, do a double check, see if there was any algebra involved or math that we needed to see. Right? We went from a bigger to a smaller velocity, and therefore our acceleration would be negative. Please let me know if you have any questions on any of this material. Take care.